Hello, everyone. Good afternoon, and thanks a lot for joining us here in this session on achieving peak performance through hardware alignment in DRA. My name is Gaurav, and I'm a software engineer at Google, where I work with the GK networking team. Recently, I've also been working on some aspects related to DRA and have been involved with this new project called DRA Net, which I'll also talk about soon.
Yeah, hi, I'm Byonggon. I'm currently working for Fluidstack. Yeah, we run large GPU plate, and we also started building lots of data centers. Yeah, that's it.
Okay, let's kick this off. So, to set the scene, your team has invested heavily on acquiring some GPU and TPU nodes. You have deployed your Kubernetes cluster on top of those GPU and TPU nodes, and you're now ready to deploy your AI/ML application. And after deploying your application, you're trying to run some benchmarks. Well, the results so far look promising. We are trying to run some standard nickel benchmarks, and it seems like the performance that you're getting is what you'd usually expect. You try to run these benchmarks again, and it seems like, well, the performance isn't consistent. So it seems like in the worst case, the performance of these nickel benchmarks is dropping to as low as 41% of what you actually could get, which is the maximum. In order to understand this, we'll have to look at a few different things. So the agenda for this meeting today is we'll first of all discuss what modern hardware topologies is, what modern hardware looks like. After that, we'll discuss the problems of misalignment, basically, how these modern topologies could influence this alignment behavior. We'll look at DRA as the solution towards solving many of these alignment issues. We'll cover a few cases where we have performed some benchmarks and discuss what those benchmarking numbers look like that are impacted by this alignment. And then we'll actually just discuss some best practices and a more future outlook on what is happening in the community right now.
Okay, before we go further, let me briefly give some overview of modern hardware topologies. So this is what we really had at the very beginning. So one CPU, one memory, it's pretty simple and straightforward. But as the demand of computing power increased, so we moved to an architecture with one shared memory and many CPUs. However, people quickly found that there was some contention between CPUs. Contention between CPUs trying to access the same memory. So in that case, performance suffers due to the memory contention in terms of latency. So to overcome this, we ended up splitting memory domains for each CPU. And this is how we arrived at NUMA. Here, each CPU has its own dedicated memory. You should point the mic to. In NUMA architecture, each domain is called a NUMA node. This is where CPU and each memory live together. These NUMA nodes are connected by dedicated fabric like QPI and UPI. But now we have a new problem. So local memory access versus remote memory access. But if a CPU needs to access memory from another NUMA node, it has to go through the interconnected fabrics. This is a remote access, and it's pretty much slow when compared with local memory access. You can easily figure out how your system looks like using command line tool like NUMA control or LS topology. This example shows how NUMA control describes NUMA locality using distance. So here, distance means the cost of memory access between same NUMA node or different NUMA node. For more intuitive understanding, here are the actual numbers. So Intel memory latency checker is a simple benchmark tool. You can see that remote memory access latency is almost twice the local memory access latency. As the real world is complex, the actual GPU box is also complicated. So GPUs and network cards those are PCIe devices, and they are connected to the CPU through PCIe switches. Here, PCIe has its own locality. Let me give you more details in the next slide. As you can see in the diagram, so communication between GPU and NIC under the same switch is usually optimized by PCIe feature like ACS. This is how GPU direct actually work, and without ACS, PCIe traffic must go up to the PCIe root port. The PCIe root port is on the PCI die. And this introduces a significant PCIe performance drop due to the additional hop. This means if a GPU and network card under different PCIe switches communicate with each other, the traffic must go through the root port on the switch, on the CPUs, and the result is significant performance drop. Again, as the real world is complex, actual GPU servers are more complicated. This is a simplified example of 4 GPU configuration server. To guarantee peak performance, we need to be aware of that there are not only NUMA locality, but also PCIe localities. But reality is be more complex since we have additional interconnect fabrics like NVLink or NV switches.
So let's look at how Kubernetes has handled this kind of complex hardware topologies in the past. Let's walk through an example. So let's say within your pod spec, you're requesting some CPU, memory. You're saying you want 1 GPU and 1 NIC. Continuing the same example, what could end up happening with Kubernetes so far is that the CPU and memory that you get is within the same NUMA node. That's good. Even the GPU and NICs that you get is within the same NUMA node, and it's also within the same PCIe root. So this is the best performance that you can actually hope for. But it's almost equally likely that what you could actually end up getting for your pods is where your process is spread across both the CPUs, it's accessing memory from one of the NUMA nodes, and even the GPUs and NICs are spread across multiple PCIe roots, and in fact, even across multiple NUMA domains as well. This is one of the worst outcomes that you could hope for. The reason why the behavior happens in this manner is because, well, within your pod spec, there's no way for you to actually say that you want your GPUs and NICs to be aligned in a specific manner. So there's no way to express this intent so far. So what that means is your scheduler just knows, okay, you just have to give it 1 GPU and NIC, and it just tries to assign one of them for you, whichever is free right now. But yes, as we saw, this is a problem, and this is where DRA comes into the picture.
Yeah, but don't worry, here is DRA for rescue. DRA is perforce-built feature to solve this problem. However, I'm not going to explain all the details of DRA and how to use it here in this session. I would recommend going to CNCF YouTube channel and search DRA there. You will find about 10 or 15 videos there. So let's take a look at the diagram. I will give you a brief understanding of how DRA solves this problem. First, DRA driver advertises resource with their locality. Second, user defines a resource claim. Resource claim is a way to describe how many resources the workload requires and the locality requirement between resources. And then the scheduler locates the right place where the requirement can be satisfied Finally, the kubelet and DRA driver collaborate to allocate the actual resources. Here, the key point is now we have a way to advertise device locality with generic scheduler, which wasn't possible for a long, long time. And we also have a way to describe user-defined resource placement. This is the biggest improvement I ever seen in this community in the last 6 or 7 years. And I'm so excited to say that we finally have DRA ecosystem. So you may have noticed that DRA itself is a collection of APIs, scheduler plugins, or controllers, or gRPC API within kubelet. But its real power comes from DRA drivers. We have seen a lot of involvement with DRA in the community, and I believe it's mature enough to call it a DRA ecosystem. We have DRA-net for RDMA network card. It brings topology-aware network card allocation to Kubernetes. And we also have a bunch of vendor DRA drivers for AI accelerators. And finally, we also have a community-driven CPU DRA driver. Each DRA driver is valuable, but combining different DRA drivers together becomes even more powerful. Which driver to combine should be determined by your workload characteristics. Here are some examples. We will show you more specific use cases and details in the next session.
Okay, so now let's look at a few concrete use cases about these alignment issues, some benchmarks, and then we'll look at a possible solution as well using DRA. The first of these use cases being the most common one, which is aligning your GPU and NICs. When this use case usually arises is when you have GPUs in different nodes which are spread across multiple NVLink domains that want to communicate with each other. Usually that communication happens through something called as RDMA, and this is usually required when you have some multi-node distributed training or inference workloads. So let's focus on one of these nodes right now and see what the intra-node topology looks like. When you're requesting just one GPU and one NIC, as we discussed earlier, the best thing that you could hope for is that you get the GPU and NIC which is perfectly aligned within the same PCIe route. The misaligned case would look something like this, where GPU and NICs have to traverse a pretty long path to actually be able to communicate with each other. Now, how the benchmark was set up was that we forced the pods into a specific pattern. In this case, we had 2 pods scheduled on different nodes, which are each trying to perform some nickel RDMA tests. To be able to properly stress the system, we actually not just had one single pod, but multiple pods running in parallel, which are utilizing each of these individual 4 GPUs and trying to test the benchmarks. Again, let's focus on one specific node out of these 2 and see what aligned versus misaligned would look like. So alignment would basically mean that all of these 4 pods would get a GPU and NIC which is each within the same PCIe route, which would look something like this. The misaligned case would be something where GPU and NICs for each pod are as far apart as possible. For example, this could be one of those pairings, the second one, the third, and the fourth. What this leads to is that there is a high amount of congestion between this inter-socket fabric or this inter-socket connection, as well as there is some high amount of congestion between the PCIe paths, because the GPU and NICs are totally far apart in different kind of domains. This is just a very simple example of the command that we used to execute, and this is the same graph that we were seeing in the beginning, which is, in the worst case, the performance drops to as low as 40% of what the maximum that you're going to get. So this is a pretty huge drop, and you totally want to avoid this. And the solution for this, thanks to DRA and the community, is pretty simple. So when you're using DRA and when you actually request these GPUs and NICs, you just have to specify a constraint which says that give me a GPU and a NIC which is aligned with the PCIe root, where the PCIe roots are aligned. So this PCIe root is something referred to as the standard attribute which the community agrees to define, and then all DRA drivers could somehow implement this attribute and expose this behavior to the scheduler. And with this, yes, you will just get this GPU and NICs within the same PCIe root. Again, I just wanted to highlight the DRA net project, which I'm personally involved with, which is solving the NIC alignment case for you. And just this morning in the keynote, the DRA net project was actually donated to the Kubernetes OSS community. So now it's actually a community-driven project rather than being hosted by a single vendor, which was Google. Let's look at another use case, which is aligning CPU and GPUs. So usually when this use case comes into the picture is when you, for example, want to copy some memory from CPU and the associated memory to your GPU's memory. The CPU and memory is usually referred to as the host. So this is copying data from the host to your GPU. In this case, what an perfectly aligned thing looks like is where the CPU and GPU are both within the same, what we refer to as the NUMA locality. And similarly, the misaligned case would be where the CPU and GPU are far apart, and for copying data from the CPU to the GPU, it has to cross this interconnect. We used NV bandwidth to test. This is some standard benchmarks available, provided by NVIDIA, to try to copy data from the host memory to the device memory and vice versa. And similarly, as we discussed in the previous example, we didn't just run one of these, but we ran like 4 of these in parallel to use all the 4 GPUs and try to stress the system as much as possible. Again, so what this would mean is that there is one pod which is utilizing CPU and GPUs all within the same NUMA node. Similarly, there's another pod which is utilizing, again, the same aligned CPUs and GPUs. Misaligned case would look something like this, where CPUs and GPUs are again spread far apart. This will lead to the congestion on this interconnect between CPUs, and what the results that we get are, well, not that surprising. The clear winner over here is that when you have perfect alignment, you get the best performance. In a perfectly misaligned state, the performance actually drops to 60% of the maximum that you can get. And just to be fair, we actually also tried to compare not just perfectly aligned versus misaligned, we also tried to compare what no alignment would look like. No alignment over here basically means that you aren't forcing any specific pattern, you are just letting things take their normal random course. And in this case, if you just let things happen randomly, and if you try to average over them, the performance that you get is still reasonable, but it's still not the maximum. So it's like almost 83% of the maximum that you could get. So ideally, you still want to get these things aligned specifically and not just rely on some random assignment. Continuing a similar example, which involves a NIC instead of a GPU, when you usually care about a NIC CPU alignment is in cases when your application is somewhat network bound. For example, you have some in-memory databases, or you have some network virtual functions where you're trying to quickly copy data from your CPU to the NIC, and this is happening very, very fast. Continuing the same example, the perfect aligned thing looks like where CPU and NIC are in the same NUMA node. Misalignment means they are in different NUMA nodes. And the benchmarking tools that we used to perform this test was iPerf, where we set up a server on one node, and then this client side is trying to communicate with this specific server. Similar to our previous examples, we are not just running one pod, but multiple pods which are utilizing each individual NIC. So that means, let's say you have one pod which is perfectly aligned, the same for the second one. We are trying to compare this aligned case with the misaligned one, where the CPU and NICs are in different NUMA nodes, and so is the second pod. This again leads to congestion between this inter-socket connect, and that means this is the results that you actually get. So in this case, the misaligned pods result in a bandwidth which is just 71% of the perfectly aligned one. Now, I do want to call out that you may be seeing over here that the no alignment one, which is where we things take the random course, is almost as good as the aligned one. Now, this is just an artifact or a byproduct of how we conducted our tests. The explanation for this is that the aligned one was so good that it was almost saturating the network bandwidth completely. What that means is if the network was more capable, it was possible that the aligned one would have been far apart from the no aligned one. So if someone is conducting this test separately, perhaps they'll see a different result. Perhaps they'll see a huge gap between the aligned versus no aligned one. But the overall outcome that I want you to take out of this is that there is still a huge difference between you not requiring or mandating any alignment versus you explicitly saying that you want these NICs and CPUs to be aligned. The solution for use cases numbers 2 and 3 is again pretty straightforward. But I do want to give this disclaimer over here that this solution requires you to use the CPU DRA driver, which is still experimental and in a very nascent stage. But still stating out what a possible solution to this would look like in the future, which is what the community is discussing, that you use the CPU DRA driver. And when you are requesting for these CPU, GPU, and NIC alignments, you could end up specifying some future standardized attribute that is something like CPU socket number. Again, this is not standardized right now. There are discussions ongoing on what this would look like, so perhaps the name could change. Other aspects could change, but the solution would look something like this.
So another use case where DRA can be practically used is multi-node accelerator placement. Multi-node scheduling is something new here. What I'm trying to highlight is that certain systems have specific topology constraint for multi-node. For example, rack scale system like GB200 or 300, or torus topology system where devices are connected to each other in multi-dimensional grid. This shows topology span constraint in GB200. You can split one rack into multiple partitions for isolation. The left diagram shows a single partition per rack domain. This means the partition is identical to the rack domain. So jobs can span the entire racks. The right domain shows multiple partitions per rack. Here it means each partition covers only part of the rack, so job spans are limited to the partition configuration. Now let me show you the practical impact of partition constraint within rack scale system. On the left, with a single partition, we can run 2 8-GPU tray jobs there, and there is no issue and no blockers. But on the right side, we cannot run these jobs because no single partition is large enough to fit a 8-GPU tray jobs. Yeah. So the practical solution here is two-phase resource allocation approach. First, locate the multi-node domain that fits your requirements or workload requirements. In this case, find a partition that has enough GPU tray, and then allocate specific resources from that domain. So I think the NVIDIA's DRA driver support for GB200 and 300 is a good example for this approach.
All right, I think we have discussed a lot of things so far, so let's do a quick recap of what we have learned, and then we'll recommend some few best practices. So the first thing that I'd like you to take out of this session is that, well, you should know the hardware that you are dealing with. You just can't be unfamiliar with the hardware that you're working with. There are common tools like NUMA-aware, NVIDIA SMI, MLC, Memory Latency Checker, LSPCI, and a bunch of them. which can help you figure out the topology that you're working with and some of the bottlenecks that you will be running into. After you know what your hardware looks like, you should be aware of what your bottlenecks are, because your bottlenecks could be different based on the application that you're running. So definitely run some benchmarks. Some common tools that would be helpful in this endeavor is NUMA-aware, NV bandwidth test, and things like iPerf.
And nickel test.
And nickel test as well, thank you. Once you know your hardware and your bottlenecks, independent of that, you should use DRA drivers or DRA as the new standard mechanism to request these specialized hardwares. DRA provides you more granular control over what kind of hardware you actually want to request. When you're requesting a subset of GPU and NICs, basically if your node has, let's say, 4 GPUs, but your pod is only consuming 1 or 2 of those, in that cases, you can explicitly say or request some alignment between your GPU and NICs using the PCIe root standard attribute. In cases where your pod is anyways requesting all the GPU and NICs which are available on your node, you actually usually don't need to specify any explicit alignment, because in those cases, the libraries or the drivers that you're dealing with most likely will take care of these alignments for you, so that when GPU and NICs pairings are required, the driver will actually take care of those things for you. So only in cases when you need subset of those, please be mindful of this. Looking into the future, some of the exciting stuff which is happening right now is, one of them just being the CPU DRA driver. This is something which the community is actively working on, and CPU DRA driver combined with some agreement on how NUMA alignment could be done would definitely help with situations where you want to get your CPU, GPU, and NICs aligned. If you want to get involved, you should definitely try participating in the working group device management. There are a couple of folks over here and the leads who are already present in this room. If you have questions, you can reach out to them or me. And if you want to learn more about DRA, there are actually abundant number of talks regarding DRA, both from this KubeCon and the past KubeCon. So they are just a YouTube search away. On the topic of interesting talks, there is going to be a very interesting talk happening right after this one in this very room on inference, multi-cluster inference, given by 2 awesome presenters, Rob and Daniel. So I will highly recommend sticking in the room for that talk as well. And with that, we totally love your feedback. If you have any questions, I think we have some time that we can take. But otherwise, thank you. You can borrow this one.
I'm curious if, looking at DRA net in particular, we've got what might be a unique use case where instead of, we've got 8 GPU systems, like H100 or whatever, but instead of plumbing up all 8 GPU NICs, we only plumb up 4 because we just don't need all 8. It costs less money. But that means now you have 2 GPUs that should be bound to a single NIC. Have you found that DRA allows you to do that oversubscription without breaking down?
Thank you. That's a great question. And yes, the answer is that DRA net, and the GPU DRA driver combined actually allow you to do that. And the way in which you can do that is basically you just say, give me, for example, 2 GPUs and give me the 4 NICs or just the 2 NICs that you requested. So this is very well a possible thing which is possible to do even today.
All right. Thank you.
All right. Any other questions? Yes, please.
I've just been really excited with all the DRA talks going on, and wondering how we can make a good case to our users that this is stuff that we would like to invest in. I really appreciated the performance numbers you showed, and I think benchmarking is a great way to start getting an idea of how much impact this might make. I'm wondering if we have a big fleet, we have a lot of GPU users, and it's hard to get them to seed GPUs for anything to us, for running dedicated benchmarks. are there any techniques or things that you can use to look at a fleet and see, hey, this is like some amount that we see a trace of misalignment causing overhead? I know you can do that with like NUMA remote memory things, but for some of these other domains.
Got it. So I definitely don't have that amount of expertise to be able to say how you can handle these kind of observability problems that you're having. I am familiar with some tooling which NVIDIA, for example, or Google for TPUs already provides, but the specifics of them, sorry, I don't think I have the specific names that you're looking for. Sorry about that.
So one thing I can add here is you're probably interested in continuous profiling. So you should do that for your GPU fleet and identify bottlenecks, and then you could think of how to get rid of that bottleneck. And here, as we shared here, you can combining some 2 or 3 DRA drivers, and it could work.
Awesome. Thank you.
All right, I think we're on time. Thank you. Thank you, everyone.